Filter. So hello everyone. Today we'll have an NPA seminar from Renee Ludlam. She's an assistant professor at Wayne State. She did her undergrad at Wayne State as well, then a PhD at University of Michigan, working on I think similar topics to what we'll be discussing today. Her dissertation won a AAS dissertation award. She then spent a few years at Caltech doing a postdoc, and just started a year or two ago at Wayne State as an assistant professor. So it's great to have Renee here. We overlapped at some of those places a little bit. We didn't overlap, but we switched places. And yeah, so today she'll be telling us about accreting around neutron stars and measuring them with X-ray observations, or observing. Okay, go ahead, Renee.
All right, thank you for the introduction. I am very happy to be here today at Yale. This is my first time here, and spurred on by looking at the beautiful buildings. I'm over by the old campus. I looked up how old Yale was, and I was actually pretty mind blown to know that it was like the early 1700s that Yale was founded. So there's a lot of rich history here that has been beautiful to see. But I'm going to be talking today how we can characterize the properties of accreting neutron stars by using X-ray observations in particular. So why are neutron stars of interest? These objects, if you don't know, are roughly about 1.5 to 2 times the mass of the sun, but compressed down to about the size of a small city. So this is almost an unfathomable amount of mass in such a small amount of space. These objects are very extreme. They are also responsible for a number of energetic phenomena throughout the universe, one such being gamma ray bursts, which is shown here. These are extremely energetic extragalactic events that are thought to occur either when neutron stars collide or you get direct collapse into a black hole from a supernova. They produce the same amount of energy that the sun does in its 10 billion year lifetime in just a fraction of a second. We also know from neutron stars that the merging of neutron stars is responsible for creating a number of the precious elements throughout the universe, including metals like silver and gold. Additionally, certain subsets of neutron stars emit pulsed emission on very regular time intervals. And from this, we've been able to utilize them to create pulsar timing arrays for different pulsars around the Earth and use them as space-based gravitational wave detectors that have been able to measure the stochastic background of merging supermassive black holes throughout the universe. And that was just released, I think, about last year. So neutron stars are responsible for a number of energetic phenomena in the universe and facilitating other research like the merging of black holes. But these objects exist in such an ultra-dense cold state that we are unable to reproduce this material in space-based laboratories. So the only way for us to understand the composition and how matter behaves under these types of conditions is by observing neutron stars. So here is showing a very simple cross-section schematic of a neutron star where we have the outermost 10 to 20% being the crust region. In this region, the density is less than that of an atomic nucleus, which I am sure you're all familiar with, 3 × 10⁻⁴ grams per cubic centimeter. So we have a pretty good understanding of the composition in this region and how the matter is behaving, because we're less than the nuclear saturation density. But once we enter the core of a neutron star, the density exceeds that of an atomic nucleus, sometimes several times over. So we don't know if in the centralmost region, the matter has frozen into some uniform state of nucleonic matter, or if we generate some kind of exotic matter, like hyperions or kaon condensates within this region, or if the quarks within the nuclear matter are able to become deconfined, and we get some kind of strange quark matter within this region, or even a combination. And the only way for us to determine what the internal combination is if we measure the equation of state, so how the pressure relates to the density. So the equation of state is just going to define how the pressure relates to the density all the way throughout the neutron star itself, from the interior to the exterior. This pressure and density is microscopic, but it sets the macroscopic qualities like the mass and the radius of the neutron star. So observationally, by measuring neutron star masses and radii, we can learn this to backtrack the equation of state. So theorists have come up with a number of models based on the internal composition and the assumption of how the matter is interacting, but it's really observationally where we can seek to find evidence to either refute or validate some of these proposed models. So here's just showing the mass radius plane for neutron stars with some different theoretical equation of state tracks traced out. The different colors are denoting the different internal composition that's assumed within these models. So blue is showing nucleonic matter, and then green is showing a combination of nucleons and exotic matter, and purple is showing some solutions for string quark matter. In the top region, that's gray, this is excluded because it's where causality is violated. This is where your speed of sound exceeds the speed of light within the neutron star, so you're unstable to any perturbations that would happen. Now, this is not all the proposed equations of state. There are so many numerous proposed equations of state to describe the matter that's internal to the neutron star, but this is meant to demonstrate the different properties based on the assumed composition. So you can see what kind of masses and radii are traced out. So from observations, we have a number of neutron stars that have been measured in terms of mass from binary interactions. So you get Keplerian parameters. And these double neutron star systems tend to align with our canonical values, about 1.4 solar masses. And you can see this doesn't really tell us anything about the proposed equation of state. All of these agree. So it's not until we get to the most massive neutron stars that have been measured to date that are above 2 solar masses that we rule out any equations that cannot produce a stable neutron star at this mass range. And this neutron star in particular is a millisecond pulsar known as J0740. This mass was measured using Shapiro delay timing constraints, but we can see that there's still a number of equations of state that agree with this more massive neutron star measurement. So it becomes clear as a field that we need to really focus observationally on getting radius constraints. This is because the radius is a slow varying function for most of these equations of state that can produce a stable neutron star above 2 solar masses. Now, there are numerous different methodologies for determining neutron star masses and radii and getting compactness of these objects. I'm going to just briefly cover some of the most recent state-of-the-art methods for obtaining neutron star mass and radius constraints. One such of these methods happens to be looking at thermal hotspots on the surface of neutron stars as they rotate into and out of our line of sight. And the light itself is therefore then under the impact of the extreme gravitational light bending near the surface of the neutron star. So this thermal light curve modeling method takes into account the different modulations that we see in the X-ray emission as hotspots rotate into and out of our line of sight. So you can see the relative flux based on the orientation of our hotspot into and out of line of sight. Now, the exact amplitude of these modulations is going to be based on the compactness of the neutron star. So here it's showing the same mass of the neutron star, but in different radii. So the more compact your neutron star is, the stronger your gravitational light bending effects are. So you're going to dampen out the modulations you see because you're seeing more of the surface at any given instant. Whereas if you have a much more radially extended neutron star, you're not able to see as much of the surface as you would prior because the gravitational light bending effects are less. So you have very prominent peaks and troughs in the modulations that you then observe. So here are the results from the first ever millisecond pulsar that was ever light curve model mapped using NICER, which is the Neutron Star Interior Composition Explorer on the International Space Station. The data set was analyzed by 2 separate teams, one US based, one in Amsterdam. They had independent models to really verify whatever constraints you get from their different techniques. And this is what is traced out on the mass radius plane for this single pulsar known as J0030. Now, what's important about these constraints is that prior to this study, this pulsar didn't even have a mass estimate. So this is kind of showing how you can get both compactness from mass and radius in systems that maybe don't prior have a mass estimate as well. What was also interesting about this study is that they could map the surface of the neutron star itself that the emission was coming from. So you can see from these two separate teams, what is important is that what I showed you on the last slide was showing a dipolar rendition of where the hot spots were. But from these studies, it turned out that these hot emitting regions were actually in the same hemisphere. So this is something that wasn't previously thought to be possible. And it tells us that instead of having a dipolar field, the field is much more complex near the neutron star surface. So maybe multipolar. Yes.
How do they know it's the bottom hemisphere instead of the top?
I think it's just the orientation of this. You're
Okay.
correct. It's just however they decided to orient it.
The hotspots don't change over time? I think that's.
Do hotspots change over time? I think they do over very long time scales, but on our human time scales, no, the magnetic field doesn't decay at that kind of rate. So this is the geometry of the more complex polar fields of the magnetic field around this neutron star solution in particular. Now this is getting radius constraints roughly at about the 8% level. NYSERDA's main mission is trying to get constraints down to the 5% level, so that just needs more data. So I will show more of the constraints from other pulsars later on, but the other more recent constraints that we have obtained was from using a different methodology, using gravitational wave events from neutron star mergers. So in this case, you have two neutron stars orbiting each other. Your binary orbit is going to shrink as angular momentum is carried away by the gravitational waves at close proximity. Near the end stages, your stars are going to become tidally deformed due to the gravitational pull of each star on the opposite star. And these tidal deformations at the end stages are then imprinted onto the gravitational wave signals, that are then observed. And those are then observed through different large baseline interferometers, such as LIGO, Virgo, and Progress. Now, the first gravitational wave event that really set off the dawn of multi-messenger astronomy was gravitational wave event of 170817. You may remember it. So LIGO had measured a very short frequency merging event, and then just 2 seconds later, the gamma ray detector on Fermi detected a gamma ray burst and correlated with the same region on the sky. So this was the dawn of multi-messenger astronomy. And from this, they were able to get some kind of constraint on the radius of the neutron star based on those tidal deformations, assuming that they were roughly the same mass when they were merging, and also some other underlying assumptions about how the neutron stars were rotating as they merged. So these are giving very complementary results when taken into context with the pulsar light curve model mapping, and I will show later on how these all merge together. But when doing any of these studies, you really want to be approaching them from multiple approaches because you want to make sure that any underlying assumptions and systematics in every approach is being accounted for, and you're getting the same results using different methodologies. So I have been, in my career, going after radius constraints of neutron stars by utilizing low mass X-ray binary systems. So these are neutron stars that have a companion star that's roughly about the size of our sun or smaller, and they're in such a tight orbit such that the companion can fill its Roche lobe and material can be transferred to the neutron star. In order to conserve angular momentum, it forms a disk of material around your neutron star system. Some of these objects can be persistently accreting, so they're always having material falling on them, creating this very luminous environment. But some systems undergo periods of active accretion, and then once the material is depleted and you don't have a disk instability to fuel more material, you go through periods of quiescence where you're no longer actively accreting material onto the neutron star. So we call those transient systems. So we study both persistently accreting and transiently accreting systems. But why? Why would you even want to study the accretion disk around the neutron star? This is because the accretion disk must truncate either at the surface of the neutron star, if not prior to it. And from general relativity, we know the definition of what the last stable circular orbit is before material must just fall onto the neutron star itself. And this depends upon the spin of the object, which is a description of the mass normalized total angular momentum of the compact object itself. So for non-rotating compact objects, your last stable circular orbit occurs at 6 gravitational radii. Now, a gravitational radius is just a way of measuring a distance, but in terms of the mass of the compact object, so you can scale it between different mass regimes. However, as you start to rotate your neutron star more, you can stabilize orbits closer to your compact object, so therefore pulling the innermost stable circular orbit closer to the neutron star surface, all the way up to the maximal range that you could possibly rotate before you overcome the neutron star's gravity. So this maximum rotation can actually move that position of the innermost stable circular orbit down to 3.4 gravitational radii. So by measuring the position of our innermost stable circular orbit, we get an effective upper limit on the radius of the neutron star itself. So we can rule out any equations that would predict a more massive radius than we are inferring. But we can also learn more about the system in general. We can learn about the magnetic field of the neutron star. We can learn about the material that's accreting, such as what is its ionization state of the medium, what's its composition, what's its density. So this technique that we utilize to measure the position of the innermost accreting region of the accretion disk is a technique known as reflection modeling. So I'm going to go over the basic toy geometry of this to keep in mind. So the X-ray emission from these systems, you have your accreting compact object, the neutron star here, your geometrically thin but optically thick accretion disk, and then hot electrons in a coronal region, which can produce hard X-ray emission. And when I say hard X-ray, just means high energy emission. So we'll see direct emission from that coronal region of hot electrons, and then the thermal emission from our accretion disk. But some of the hard X-rays can irradiate the disk and be reprocessed by the material and re-emitted, giving us what is known as the reflected spectrum. So here is the overall distribution of photons that we then observe. So here is showing the X-ray energy range on the x-axis. On the y-axis is the flux per energy bin, just multiplied by that energy bin squared. So it's easier to see the relative contribution of each component. So again, we have our thermal accretion disk, the hot electrons from the corona emitting in the form of a power law, and the reprocessed emission from the accretion disk. And you can see there's this really prominent feature at roughly about 6 to 7 keV. But in these systems, because the neutron star has a surface, we can also have emission from either the neutron star itself, which is thermally driven, or perhaps there's a boundary layer region, which I'll talk more about later, between the inner edge of the accretion disk and the neutron star surface that emits in the form of a thermal component. So this thermal component can also irradiate the disk, be reprocessed and re-emitted. So you can see here, this gives us an overall different spectral shape. So you can see we now have a thermal component instead of that coronal emission. And this is much spectrally softer, as we say, because it's all tending towards low energy X-rays versus the hard X-rays of at higher energies. But we still have this prominent emission line feature at about 6 to 7 keV. Now, this emission is due to iron shell emission. So iron is one of the most tightly bound elements, so it can keep its inner shell electrons in these highly energetic environments close to the neutron star. So I'm sure you're all familiar with this, right? Your photon comes in, bumps your electron up to a higher energy level. After some time, it'll decay and re-emit a photon that's specific to the difference between those energy levels. So specifically what we're looking at here is the iron K shell emission, so the innermost shell, between about 6.4 to 6.97 keV, just depending on the ionization state of the material. Now, this line emission is intrinsically narrow when it's emitted, but it becomes broadened due to different effects within the innermost accretion disk. So this blue annulus is just showing an accretion disk and the emitting region in which the line is coming from. So it's intrinsically narrow when emitted, but due to Keplerian motion, you're going to get a two-horn profile. Then due to the rapid rate which the material is moving, some of this is going to be beamed into and out of our line of sight. And this gives us the overall skewed shape. So you have blue shifted towards us, red shifted away. This is all in terms of the observed frequency over the emitted. Then because you're in a large gravitational potential well close to the compact object, your photons are going to lose energy as they leave the system. So you're overall gravitationally redshifting this line down to lower energies. Now, if we take an emission region closer to the neutron star, you can see that all of these effects become much more pronounced. So this is shaping the overall line profile that we then observe with our different missions. Particularly, the degree of broadening that we're measuring in the red wing, or how extended the line is to low energies, tells us how close we are to the compact object itself. Then we can learn something about the inclination of the system from looking at the blue wing, so the part that's blue shifted. So as you look at a system more face on, you're not going to have much of those Doppler shifting effects. So you're going to have a steep drop in your line profile towards higher energies. But if you start to look at systems that are more inclined, you have more Doppler effects at play, and therefore you're going to broaden this out to higher energies. So I have been combining data from different advanced X-ray observatories, one being NuSTAR, which is a nuclear spectroscopic telescope array. It has this large 10-meter deployable mast that allows it to focus in hard X-rays for the very first time. So we have a passband from about 3 to 80 keV. Then I couple this with data that can be taken with NICER, as I mentioned before. This is a mission on the International Space Station. It's about the size of an industrial dishwasher. Yes, dishwasher. And it has an energy passband from about 0.5 to 10 keV. So we can couple the hard X-ray emission with the low energy emission to reveal all the emission from a broad X-ray spectrum to really determine which of those different components that I've shown you in that toy model are at play. And particularly by combining these emissions, we get more photons that are collected in that iron energy band that I had talked about. So really being able to measure the Doppler shifts and the broadening from the relativistic effects. Okay, that was all the background. So now I'm going to show you what we can do with this kind of modeling. The best source to demonstrate what kind of constraints we can get using this methodology is looking at one such object known as Cygnus X2. This has a binary orbital period of about 9.8 days and an inclination about 63 degrees. So because of its inclination, we see periodic dips in the optical light curve. And from that, you can measure the Keplerian parameters and determine the mass of the neutron star. So this has a known mass of about 1.7 plus or minus 0.2 solar masses. So since it already has a mass, it makes a good candidate for going and getting complementary radius constraints. So what we did is NuSTAR observed the object on 3 different occasions, 2 of which we had complementary data from NICER to really get better statistics in the iron band. I think this will be a little lost on you all since you aren't in the field of astronomy, but doing X-ray observations of like AGN and such, you get maybe like 10 counts, right? You get very, very limited amount of statistics. Here we have greater than 1 million counts per spectrum that we are analyzing. So we are not photon starved by any mean. We have really good statistics. I went through and I analyzed the data using 2 independent models to describe all the emission. I also used 2 independent models to describe the relativistic effects. So I wanted to make sure that any results we got weren't biased on our choice of models. And what I found is that the innermost accretion disk remains consistent with that innermost stable circular orbit, so roughly between 6 to 7 gravitational radii. Now here I'm making a conservative estimate, and I was assuming that the neutron star is not rotating. Remember, if we assume rotation, we can move the disk closer to the neutron star. There's a lot of uncertainty about what the angular momentum of a compact object is, and I can talk about some estimates that would show better constraints if we take into account some back of the envelope calculations later on. We also determined from measuring the relativistic effects of that line profile, the inclination of about 67 degrees, plus or minus 4 degrees. So that's at least a consistent answer with what you got through optical estimates. So it's kind of an independent check to make sure that we're getting the correct solution. So what does this mean? So if we return to the mass radius plane that I showed before, we can convert that gravitational radius into a physical unit, given that this system already has a known neutron star mass. So we get an upper limit of about 19.5 at the high mass end for the neutron star's mass, and about less than 15.3 at the low mass end. This is all an effective conservative upper limit. Remember, I'm assuming zero spin. We can compare this to those constraints that I showed from pulsar J0030 earlier on from those two independent teams. Then NICER also, like her model, mapped a second pulsar, the most massive pulsar that we know to date, above 2 solar masses. And these are the constraints from those same two independent teams. You can see there's quite a bit more of a range than that 8% level for pulsar J030. Lastly, we can overlay the constraints from gravitational wave constraints, such as the binary neutron star merger of 170817, as well as the candidate 190425. So this is a very messy plot, right? There's a lot of different regions that are traced out. But it's important to note that in order for any equation of state to be viable, it has to pass through all of these measurements, right? They're all independent measurements with their own sets of systematics. So we want to be approaching this with multiple different methodologies. And again, the radius constraints from reflection modeling currently are at a very conservative level. So we're not able to rule anything out on its own, but it does serve as an independent check. I can talk later at the end, if anybody wants to ask about what we can do better in the future and how we could push down this radius constraint. So this is one methodology for determining neutron star radii. But as I mentioned before, we can learn a lot more than just neutron star radius. There are a number of different accreting neutron star systems that have been observed, and we have undergone this reflection modeling constraints, and we can now create a sample in which we can draw inferences about the properties of these systems. So there's well over a dozen to create this sample size. One thing we can look into is how the position of the innermost region of the accretion disk changes as a function of mass accretion rate. So the presence of having reflection features inside these neutron star systems suggests that there must be some kind of similar accretion geometry occurring between black hole systems and neutron stars. Reflection, these iron line features were first discovered in AGN in the 80s, and then not till recently in the early 2000s for stellar mass black holes in our own galaxy. And then it wasn't until about 2007 that they were found for neutron star systems. So for black holes, it's generally assumed that the disk remains close to your compact object when you have high levels of mass accretion rate, so inflowing matter. But it's thought that as your mass accretion rate drops, your disk recedes until roughly you reach about a level of 1%, the Eddington limit, Eddington being just the maximum rate that you can accrete matter before radiation pressure dominates and drives away any kind of accretion flow. At 1%, below 1%, it's thought that your accretion material transitions from that geometrically thin, radiatively efficient regime into something that's much more extended and radiatively inefficient. So that begs the question, does this same trend hold true for neutron stars? So here's showing the position of the innermost accretion disk in terms of that innermost stable circular orbit versus the Eddington fraction, which is just a proxy for mass accretion rates. It's the luminosity of the system divided by that maximum Eddington luminosity. Here we have a number of different neutron stars that have been observed using new stars, some of them complementary with NICER, and applying these reflection model techniques. So you can see we're spanning a very large range from below 1% of Eddington all the way up to the Eddington range. At the lowest mass end, we can see that there are some sources that are able to remain consistent with the innermost stable circular orbit below about 1% of Eddington, where typically in black hole systems, you become radiatively inefficient. So this tells us that we are able to produce stable, radiatively efficient below 1%, but there has to be a transition region. So this is still an active area of figuring out when does this transition occur within these systems. And we can see that above 1%, we don't have that clear one-to-one correlation. There's a lot of scatter on this plot, right? We're not seeing that at the lowest end, the disk recedes, and at the highest end, the disk is consistent with the innermost stable circular orbit. There's a scatter all over. And this isn't unsurprising when you think about black holes having a surface. All matter that falls into them is lost from us. With neutron stars, we have a surface. We have an intrinsic magnetic field. This is going to complex the situation and the geometry that we're looking at. But what we can do is we can use the information that we see here of the position of the inner disk not being at the innermost stable circular orbit to place limits on the magnetic field strength. So if we assume that the radius we're inferring corresponds to the Alfvén radius, which is the radius at which the magnetic pressure is balanced by the ram pressure of the material inwards, we can effectively place an upper limit on the magnetic field of the neutron star itself. So these blue points are showing the magnetic field estimates from reflection modeling using the reprocessed emission, inferring an inner disk radius, assuming that's the Alfvén radius, you get a limit. In black is a comparison to points for accreting millisecond X-ray pulsars. So these systems, accreting millisecond X-ray pulsars, exhibit pulsations. And these pulsations indicate that you have material being channeled along magnetic field lines to the neutron star surface. In these blue data sets, we don't see any pulsations. So we don't have that smoking gun telling us that indeed we have magnetospheric accretion. But that could be perhaps the reason we don't see it might be just an imparted by perhaps we have shielding of the material. So we're not seeing the pulsations because there's so much material around it's being shielded from our line of sight. Perhaps orientation is such that the poles that the rotation pole and the magnetic poles are aligned, so we wouldn't see these modulations, which you need to be away from the poles. But importantly here, showing that we are on the correct track is the star points. These star points is a known accreting millisecond X-ray pulsar. And in our data set, we don't see pulsations, but we know the system has a strong magnetic field and we're getting the same estimation as when done from using the pulsations. So this is showing us that we can actually use these secondary indications to get some magnetic field strengths. But because we don't see pulsations, it's not improbable that perhaps some other effect is at play. Perhaps we have a boundary / spreading layer on the neutron star surface that is impeding the accretion flow. This layer is the region where the rapidly spinning material from the innermost accretion disk has to slow down to the same value as the slower spinning neutron star. So in this region, you have radiation pressure domination, your gas is unable to cool efficiently, and you get this vertically and radially extended region itself. It's difficult to constrain this observationally. It emits like a thermal component, but we know there are other aspects of the system that emit thermally. So how do we disentangle this? How do we get some kind of indication of which of these factors are at play? What we can do is look at the position of the innermost accretion disk as a function of mass accretion rate in these systems. This is because the boundary layer and the magnetic field act in a very different way. In terms of the boundary layer, this is showing the radial extent of the boundary layer as a function of mass accretion rate, or in terms of the luminosity of the system. And what you can see is that as your mass accretion rate increases, more material is dumped onto the neutron star, you're going to make your boundary layer region bigger, more radially extended. So that just shows us that we have a correlation where your inner disk radius would move out as mass accretion rate increases if you have a boundary layer in a given system. Conversely, as you increase your mass accretion rate onto a magnetic field, you're going to have more ram pressure, so you move the disk inwards. So because these act in an opposite manner, if we can observe a system we know is truncated over a number of different observations that happen to probe different parts of its luminosity, then we can determine if the magnetic field or the boundary layer is at play. Now, I had talked about how at the lowest mass accretion rate regime, we can try to probe any changes from radiatively efficient, thin disk, to something that's radiatively inefficient. We have some evidence that this change in accretion occurs. And one such source that tells us that there is this variation in the accretion flow comes from 401608. This is a transiently accreting system, so that's why I introduced transiently accreting systems. So it undergoes periods of active accretion roughly every 2 years. So this is showing the long-term light curve. So MAXI is just an all-sky monitor on the International Space Station. And this is normalized to the time of the outburst to kind of put all the outbursts from 2014, 2016, and 2018 on the same plot. NuSTAR observed the source as it decayed. So the source would undergo active periods of accretion, it maxes out, and then your accreting material is depleted, so you're going to just decay in your accretion flow. It observed the system at the end of its outburst in 2014, and there was another initiative to do this again during the 2018 outburst. And you can see here the differences in the maximum intensity that the sources were observed at. In 2014, the spectrum that we observed showed reprocessed emission features. But when we looked at the end of the decay in 2018, there was nothing. Now, these are single observations, so you have no inclination of what the properties of the system were prior to that one observation. Luckily, NICER was observing the source throughout its outburst. So here is showing the different observations. So we have a rise, we have some data at the peak, we have some data throughout the decay process. So we can extract spectra from each of these different epochs to determine, was there reprocessed emission in the system at all that would have indicated that there was a change in the accretion flow. If there wasn't, then that just means that in this specific outburst, there was no reprocessed emission. Maybe that has something to do with the disk just being too far from the neutron star to begin with. So here is the results when we take the spectrum from these different epochs. So we have the rise all the way down to the middle of the decay, and then we can compare it to the NuSTAR observation 2014 to see if they show a similar shape. Remember, in 2014, we did see reprocessed emission features. You can see that iron line profile in all of these different observations. So there was reprocessed emission. We did have standard thin disk accretion that was radially efficient. But at the end stages, there is no emission components. To create these ratio plots, we just apply a continuum model. So it's just taking into account all the direct emission you would see. And we do not apply any models for the reprocessed emission. So when you take the ratio of that, your reprocessed emission should just pop up. So the fact that there was emission from reprocessed accretion in the accretion dose, and there's not at the end stages, tells us that there was likely this change in accretion flow from radiatively efficient thin disk to something that's radiatively inefficient. We tried different models just to see like, oh, maybe the disk just moved out. Maybe you're just too far away to have these features. And you can't explain the lack of the emission features. You would still see some narrow emission line components if that were the case. We also checked that it wasn't a signal to noise issue, right? If you don't have enough signal, it's just going to look like noise, right? Wasn't the case either. And this occurred roughly around 0.2% of the Eddington limit. So somewhere in this range is where we transition. We need more observations at higher cadences to really determine where exactly this occurs and in more objects. Now I'm going to move on to the last major portion. This is talking about a subset of X-ray binary systems. I talked about low mass X-ray binaries. There's a subset known as ultra compact X-ray binaries. They have orbital periods of less than 90 minutes. And if you have a neutron star in that type of orbital period with a companion, you know that your donor star must be also degenerate, like a white dwarf, or perhaps a bare helium star. So I talked a lot about the iron line component because this is the most prominent feature when you have standard solar abundances. But if you're now accreting from a white dwarf, you have a lot of carbon and oxygen in your accretion disk. So now you have this very prominent low energy emission line in addition to the rest of the reprocessed emission that you see. And this is important. We can learn things from having multiple emission line components, which I will talk about. Oh, that's just labeling them for you. Okay, so you can see there's two different data sets. We have low energy emission from NICER, high energy emission from NuSTAR. And we can model the spectral distribution of the photons using those toy models that I talked about before. So you still have that prominent coronal emission from hot electrons. We have thermal emission coming from some black body components. And then we have the reprocessed relativistic reflection component. This is just showing the residuals in the bottom portion to show how well our model is doing. So from modeling the relativistic reflection model, we can get some kind of constraint on the location of the inner accretion region. We found it's very consistent with the innermost stable circular orbit. Here I've already converted into kilometers. This does not have a known mass, so I used a canonical mass, about 1.4 solar masses. So we get an inner disk radius about 12.4 to 13.3 kilometers. Still assuming zero spin. Don't really know the mass of the neutron star. I'm just going to walk you through how these can be useful. However, we have black body emission. We know thermal emission from a black body can be characterized in terms of its luminosity component and give us some kind of radius constraint. If we assume it's spherical emission, we get a very small value, about 3.4 kilometers, and that is way too small to be the surface of the neutron star. That would have been definitely in the region where causality is violated. So it's probably not spherical emission, but instead this tells us about a different aspect of the system. So we can use these components to build up a coherent picture. So again, we have our accretion disk around a neutron star. If instead of spherical emission, we attribute this thermal component to narrow banded emission, which would be typical for a boundary layer component, and assuming that the height of this region is about 5 to 10% of its radial extent, we get a much more conservative value of the constraint from the thermal component using a banded emission of about 11 to 15 kilometers. This is now in agreement with what we were seeing from the relativistic reflection modeling. But as I showed before about the property of the black body, we can also get some estimation of what the radial extent of this region is from the surface of the neutron star itself. That depends just on the mass accretion rate of the system. So plugging in the values for the time of our specific observation, we get a maximum radial extent of the boundary layer for this object from the surface of the neutron star. You don't have to know the radius of the neutron star beforehand. Is roughly about 1.2 kilometers. So if we combine this with what we know from the reflection modeling, we get a maximum upper limit on the neutron star of about 12.1 kilometers. So this is another way we can use all these various components to build up a coherent model of these systems. Now, in this case for 401543, when we plot the profile of the iron line to the oxygen line in terms of its velocity space, so taking the energy component over the centroid energy, we see that these have a very similar broadening component. So that suggests they're arising from the same region in the accretion disk. But it's not clear if this is the case for all ultra-compact systems. It'd be important if we could constrain that perhaps the oxygen line comes from the same innermost accretion disk as the iron line, because there are some systems where there's no iron line present, but we see an oxygen line. And if we can definitively say we know this is coming from the innermost accretion disk, we have a secondary method of determining the neutron star radius. These oxygen lines are also important in terms of the telescopes that are available. So this is the effective collecting area, so the number of photons we can collect, versus energy. And you can see with NICER, the oxygen line occurs closer to the peak effective collecting area than iron does, right? So we'd have more statistical photons in which to do these kinds of studies by looking at the oxygen line component. Plus, we were able to see the entire reprocessed reflection component. So with this, we can do multiple different kinds of investigations. So we can get additional constraints on the position of the inner disk in the cases where an iron line isn't there, or even if it is, we'd still have better statistical uncertainty. Then, if it turns out that the oxygen line is not arising from that same region as the iron line in these systems, what we can do is learn more about the disk structure itself. If the radius of the iron line component and the oxygen line component are statistically distinct, and well as the ionization of each of these materials, then we learn what the ionization is as a function of radius throughout the accretion disk for the first time. This has never been mapped before. If it turns out that they are coming from distinct radii, but the same ionization zone, then this tells us that the illumination source geometry of that coronal region is much more extended than what is typically thought to be a compact emitting component. So I'll conclude, and then you can ask any questions that you would like. But I hope I've convinced you that reflection spectroscopy is a very valuable tool for learning about the properties of neutron stars, but also providing complementary, independent constraints on neutron star radii by providing a conservative upper limit currently. By capturing these multiple emission line components by utilizing either ultra-compact systems or otherwise, we can really shed light on accretion disk properties, such as how the ionization changes as a function of radius, or what the emitting geometry is of our compact coronal region. Now, understanding neutron stars and the accretion around them is very much an active and ongoing area of research, but this will undoubtedly be aided by the recently launched X-ray mission known as XRISM, which has superior high energy resolution of about 5 eV, which has never before been able to be launched into space. Additionally, this could be aided by any kind of X-ray polarization measurements. So there is a mission known as XP that does polarization of X-rays. This is also complementary to reflection spectroscopy in building up a coherent image of these systems. And there is much more on the horizon with NASA's probe class mission concepts that have been submitted, as well as Athena coming by the European Space Agency, which is set to have an even larger high energy resolution array than what is currently available with XRISM. So it's really an exciting time for X-ray astronomy to learn more about accreting systems. So I'll take any questions that you may have.
Okay, questions for Renee?
So with your neutron star and companion like system, when they're orbiting each other, does that introduce like modulations to the signal that affect like your transient
Yes, that's a really good question. And so there are systems where that does impact what times that you can extract data from, right? Because you're going to have, like you just mentioned, X-ray eclipses as your companion star moves along your line of sight. So those are very highly inclined systems where we're looking at them kind of edge on. But you can actually do so much more in those systems, right? Because there's going to be periods of time where you're actually looking through the material of the companion star. So when you're coming in and out of eclipses, you can learn about the interactions between where the accretion disk is forming down to your compact object. But when you're outside of those eclipses, you can just take the data like normal and analyze them as well.
How's the boundary layer supported? Like it seems so it's inside the innermost stable orbit radius, right? So why is it there and not like plunging into the neutron star?
Well, it is on the neutron star surface. It's extending from the neutron star surface. So it's all the material that's come from your accretion disk down to your neutron star surface. And this is the region the boundary layer is. It's extending from the surface of the neutron star where it's radiation pressure dominated and cooling inefficiently. You have viscous effects and differential rotation as you move from the most rapidly spinning material that just came from the disk down to the neutron star slower spin. So you get this very radially extended, vertically extended system.
So for most of this, you assume that the neutron stars had no spin. Is there a way to like either independently determine what the spin is, and then you could maybe get better limits on the measurements you're taking?
I love that you asked that. Thank you so much. Okay. So yes. So how do we get some kind of constraint on the dimensionless spin parameter? One way that we can do so is if we know the spin frequency of the neutron star, and there are different ways to know the spin frequency. You can either look at, on some neutron stars, when you have enough material that has accreted onto the surface and you can undergo thermonuclear runaway, those are known as type 1 X-ray bursts. So you have a thin layer of hydrogen and helium that undergoes thermonuclear burning very rapidly. During the initial parts of that burning, it starts off as a spot on the surface and then consumes the whole neutron star. during that period of time where it's a spot, it's rotating, right? So it acts almost as like a millisecond pulsar. It's a pulsation that we can observe. So that would give you an indication of the spin frequency during the burning, thermonuclear burn-in. There's also quasi-periodic oscillations in the data. So these oscillations are like packets of material moving in the system that emit at a specific frequency. And so there's theories that perhaps if you measure these QPOs, the difference between certain values indicates the spin frequency of the neutron star. That's a little bit more uncertain. There's a factor of 2 difference. But if you take that, you can learn about a constraint on what the dimensionless spin may be. And this is because your spin frequency is related to the angular momentum of the compact object itself. But then you need to know the moment of inertia. The moment of inertia depends upon the equation of state. So then you have the added uncertainty there in that case, right? Different equations of state are going to give you different descriptions for the moment of inertia itself. There are some approximations, such as perhaps we take the T7 approximation. It's a quadratic variation of the mass energy density within the neutron star, and it agrees pretty well with a lot of the existing equations of state. So it's close as an approximation. So if you take that and you take the spin frequency tentative estimate for Cygnus X2, that one source that I had shown, this is taking the difference in kilohertz QPOs. So this is, again, could be off by a factor of 2. But if you just take it as a way to show what kind of constraints you could get better, if you know some kind of estimation for the spin frequency. So this gives us a range between about 0.06, so we're inconsistent with 0, right? I mean, neutron stars are rotating. 0 is a little bit extreme and conservative, all the way up to about 0.36 approximately. So what would that mean? Let's go through this. Right, this is what we had before. Now, if we take just that small change from 0 spin to 0.06, we shave off a little bit in terms of our upper limit. If we go all the way to that higher end of 0.36, we can shave off nearly 2 kilometers in our upper limit and now become way more competitive in terms of our constraints. So hopefully, nobody else has another question. Hopefully in the future, one of the ProClouds concept missions known as HEXP, which is the high energy X-ray probe, has enough sensitivity to actually trace out gravitational radius solutions. So this is because when we were doing our simulations, it's drawn from random photon seed distribution. We had to do it a number of times. We did it like over 10,000 times. And you can see that each time you're pulling out a very specific solution. So this is, if we had a spin 0, you can see everything is pretty centered along 6 gravitational radii. Here is moving to about a modest value of 0.17. And you can see we're shifting slightly. This is still the 6 gravitational radii. We get to the most rapidly rotating, typical for neutron stars in our galaxy. You can see, well, it's hard to see, but we actually rule out a dimensionless spin of 0 in this case, and everything tends towards the actual value that it turns out, which I think is about 5.2 gravitational radii. So these were the constraints that we had obtained. In terms, the colors have changed now, but here is with the nicer new star study that I had published with a 6-dimensional spin. Here are the constraints that we get with a free dimensional spin. Currently, with our best available data sets, you cannot leave your spin free because they're degenerate parameters, right? The spin sets your ISCO, your innermost stable circular orbit. But we'll have enough energy resolution and photons and a large broad passband to actually be able to measure both the inner disk radius and the dimensional spin parameter of these systems through data alone. Sure.
Then we can end there. Thank Renee one more time.